Vinay sir is there, right?
Yes, sir. I don't know.
Yeah, Dr. Shikhar, am I audible?
Yes, sir, you're
Yes, sir.
audible,
You're
sir.
audible, sir.
Yeah, thank you, thank you.
Uh, Thanks, sir. I just okay. Sakshi.
Yes, sir. Sure, sir. We'll start now.
Yeah, you can start now.
Okay, sir. Good evening, everyone. I'm Sakshi Purswani. On behalf of the Department of Statistics and Data Science at Christ, deemed to be University, Yashwanthpur campus, I extend a very warm welcome to all the participants, resource persons, and esteemed guests joining us today for this national level faculty development program on advanced statistical techniques for academic excellence in data analytics 2024. This 7-day program, designed to bridge the gap in advanced statistical methodologies, promises to enrich us with key insights into data analytics and its applications in academic excellence. Over the course of this program, participants will dive into critical topics such as time series analysis, regression, machine learning, generalized linear models, survival analysis, and much more, guided by a distinguished panel of experts. I now request Preetha Chaudhary to take over the virtual platform and introduce our support team. Over to you, Preetha.
Thanks, Sakshi. Let me take a moment to introduce the esteemed support team behind this program, whose encouragement and guidance have made this workshop possible. Dr. Father Benny Thomas, our director, whose leadership has been instrumental in fostering a conducive environment for academic growth. Dr. UKP, associate director, whose support always guides us to reach the goal. Dr. Father Vinod Michael, campus administrator, for his dedicated involvement and contributions. Dr. Jovi Thomas, our dean, for being the pillar of strength and inspiration for this program. Dr. Raghunandan Ji, associate dean, for his valuable input and consistent encouragement. Now, moving to the core organizing team. Dr. M, head of the department, has played a pivotal role in steering this program as part of the advisory committee. Shikhar Tyagi, assistant professor and convener of this program, whose tireless efforts have ensured everything is in place for a seamless experience. Dr. Gobinath R, associate professor and the organizing secretary, whose insights have shaped the impact and relevance of this event. Dr. Lakshmi Basappa and Dr. James, both assistant professors and key members of the advisory committee. We also have the energetic technical team of Rahul Agarwal and Mahi Vivi, and my fellow student coordinators, Sakshi Purswani and Rahul Samuel Noronha, who are ensuring the smooth execution of the program. I'd like to request Dr. Vinay M, our head of the department, to address the gathering and share a few words of encouragement as we embark on this exciting event. So,
Good evening, everyone, and thank you for being a part of this national level faculty development program. And encourage, I think it's a happy moment for us that we are organizing this kind of a program for ensuring that we are up to the mark in the industry right now. From the student, scholars, research oriented people, faculty members, all the people who are interested towards moving towards in statistics. Early days, I think we were only thinking that only few people who are interested towards statistics will learn that part, not everyone. It is not cup for everybody and it is not for us. But when we started moving towards these advancements, and now we are moving towards this deep learning, AI, machine learning, everyone have understood that statistics is now the bread butter for every of these things at all. We have to be ensuring that knowing these knowledge from the scratch to the advanced level ensures that creating a better LLM models, creating a greater applications, solving a problem in the industry is very much encouraged by all of us right now. Thinking that in the mind, we also wanted, earlier we had some conflicts of like what time we are supposed to do this faculty development program. Should be in the working hours or should be in the weekends or should be in the evening time. finally we have come to the place that's where all of us, after our class hours or maybe after our duty, after our responsibilities, we are spending our time for the next 5 days on every day evening between 6 o'clock to 8 o'clock. Ensuring that, I think I would like to thank you, all of you, for keeping yourself free during this time and attending this kind of a program. Shikhar Tyagi, first time when Dr. Shikhar came to ask me, so this is a plan, we would like to go ahead with a team of people, we would like to work. I was very happy to see that the knowledge has been sharing from a great resource people, from a research oriented, from an industry experts, and the practitioners who are doing really these statistics works are coming to the online and then sharing their experiences, not just the theoretical lecture, but also a demonstration, a practicals as well. See, if have a data, it's not sufficient in nowadays. Even like a tools like a Power BI helps us to create a dashboard and then encourage them the applications to showcase. This is the platform what we are looking at right now. This is just the beginning, but we are trying to give a platform for all students, researchers, faculties, and all the members who are right now, all the people who are participants who are in part of this. Take this as an advantage. Embrace yourself to ask more questions and then getting a more knowledge from the resource people, have an interaction, have a great network, and we will be moving towards learning more things. Happy learning, and thank you, and best wishes to everyone. Thank you.
Thank you, sir. Heading further, we are delighted to welcome Professor Dr. R. Vishnu Vardhan, Assistant Professor in the Department of Statistics at Pondicherry University, to our online faculty development program. Professor Dr. Vardhan holds a PhD in statistics from Sri Venkateswara University and has over 4 years of academic and research experience. His areas of expertise include biostatistics, multivariate analysis, and statistical computing. Professor Dr. Vardhan has published over 60 research papers in prestigious journals and has made significant contributions in areas such as classification techniques, ROC curves, regression models, and machine learning. He has been an invited speaker at various prominent conferences and seminars and has earned several accolades for his impactful research. In addition, he has guided numerous PhD scholars in their academic journeys. Today, Professor Dr. Vardhan will lead us an interactive online session on regression analysis, clubbing with a hands-on session using R. Please join me in welcoming Dr. Vishnu Vardhan to this virtual platform.
So shall I resume? Start?
Sure, sir.
Yes, sir. You can start.
Yeah, yeah. So good evening to one and all. At the outset, I'm very much happy to be associated with this faculty development program. I should say my thanks and best wishes to Dr. Shikhar, who has been continuously interacting with me and contact with me to discuss about this activity. And apart from this, we are regularly working on some exchanging of activities also. So I should say I take this platform to thank him for that, extending his support in another academic activities where I do reach him out. Okay, and my best wishes to the department and the head, Dr. Vinay. So has been it is understood that it is well cooperated team and it's a good coordinating team. Without that a leader or kind of a leader efforts, the execution will not come into in this particular place. Okay, and with the transition of time, we have to go with that, and I'll try my best to reach you out in the designated time and the designated topic which is given to me, that is regression analysis. And basically I'll divide the concepts that I'll be covering as at a simple level and at a multiple linear regression. So initially I start with a little theory, not dwelling into much of the mathematical orientation, but at the same time, without sacrificing the basic requirements of understanding the regression concept, I'll cover that, and then I'll go with a demonstration with R. I have taken some data sets which I can share with Dr. Shikhar, that can be given for exercise as well if needed. Okay, so for some time I'll use the graphic tablet to explain something, and then I'll go with our demonstration. Hope my voice is clear. Is it audible, right, as of now?
Yes, sir. It's
Yes,
Yes.
sir. Yes, yes.
Yeah. And currently, I am working as a professor in statistics department, Pondicherry University, which is a central university. And besides this, I am also deputy coordinator for internal quality assurance cell in Pondicherry University. Word document is in?
Yes, sir.
Yeah, fine. So the topic that we are about to start is regression analysis, which is quite interesting and very much important in statistical data analysis. So as a statistician, now whenever we face the data, I say like this, whenever we face the data, we think a lot intuitively that what we can do with the data. What sort of analysis that can figure out or that can make out from this particular data, any kind of a data. For example, let me start with a study like this. Let me take this example now. This is one kind of interesting example that I take mostly, that this is the data set of sleep health and how the lifestyle is. Now, when we face this kind of a data, or when we just come across this kind of a data, immediately any practitioner has to dwell into to see that what sort of a variables, that means what type of variables that we have in a data that we have, right? So now when we see this, we have a nominal data, and then this is a continuous data, and occupation again it's a nominal data, and then sleep duration, quality of sleep, physical activity. Like this, there are many other variables which are on a quantitative measurement, and then BMI category is again nominal data. And finally, we have one more column which is nothing but a sleeping disorder, like no sleeping disorder, insomnia, and then this sleep apnea disorder. Okay, so that is what we call sleep apnea disorder. So there are 3 different categories here. Now, no disorder. Now, when we look at this, first look of the data, what we can do, what sort of objectives that we can phrase, right? So the thing is, directly, most of the people, when they come across this kind of a data, most of the people, what they do is, okay, I have a category where sleeping disorder is there, where no disorder, insomnia and sleep apnea. So I can build a classification model. Right? Is it the case all the time? I say no, because among many machine learning algorithms, for every data, we cannot directly jump into modeling aspect and then bring out some machine learning, classification rule, and then bring out some allocation strategy, validate the model, and so on and so forth. Now, generally, the basic idea for any statistician or any practitioner is that instead of directly jumping into a modeling aspect, what anyone has to look into. That means they have to spare or they have to spend a lot of time on visualizing the data. That means make use of all the continuous variables or make use of all the quantitative variables that helps us to understand the patterns that are available in the data. Now, is it only patterns? What other things that we can look into the data? apart from patterns, we can get some more information that how they are related to each other. That means, for example, let us take like this quality of sleep, how far it is related, in what way it is related to sleep duration, how stress level is related to quality of sleep or sleep duration, the number of daily steps that I take, how far it is related to my quality of sleep. And then among all the quantitative measurements, how the relational intensity is getting constructed. Right. So this is one thought process that gets generated, that how we can quantify the intensity or the degree of relationship among the quantitative variables to know that the amount of information that is getting generated out of this particular graphical representation. So when there are more than two continuous characteristics are available, or when there are two characteristics, continuous characteristics, generally we go with a scatter plot and then see how the magnitude is there and how the data points are spread across and how the distribution of data points is there. Like this, so on and so forth, we look into many aspects. Now, can we bring the same structure when we have more than a pair of independent variables or when a pair of variables? Yes, naturally we can do that. In what way? It is nothing but your matrix scatter plot. So using matrix scatter plot, one can generate a pair of scatter plots which will tell different relations among the interested variables. Now, the next question comes that when we, let us take, we have generated a set of matrix scatter plots. Now I need to see, this scatter plot is in a general sense. Now I want to make use of one particular variable, which is a categorical one, and impose that categorical variable into that particular scatter plot to see the distribution of the categories of that particular categorical variable, how it is spread in that particular 2D scatter plot. That means, for example, if I want to see the distribution of the varieties of sleep disorders and then taking the scatter plot between sleep duration and any heart rate or physical activity or quality of sleep, then I see how the cluster of points are coordinated or spread across in the 2D axis, given the labeling of no disorder, insomnia, and sleep apnea. Now the question comes, why I have to do this kind of a presentation? Will that be a meaningful thought? That means whatever the intuition or intuitive way that we go with handling the data, presenting the data in a graphical way, or applying a statistical technique, it should have a rationality. It should have some kind of a meaningful outcome. Now, the example what I have taken, or kind of an illustration, oral illustration that I have told, that taken sleep duration on x-axis and quality of sleep on y-axis, and embossing the categories of sleep disorder in the 2D coordinate, what I will get? What sort of information that will reflect on the graph? Is it people with no disorder have a high sleeper duration with high quality of sleep? People who have sleep apnea disorder will have a less sleep duration and a less quality of sleep. People with insomnia will have a high sleep duration but less quality of sleep. Like this, I can easily trigger out, or I can easily make out or expose the patterns across different categories of final outcome variable. So now let us come back to my statement that directly we should not jump into modeling aspect. First, we should spend a lot of time before we create a classification rule. we have to spend a lot of time in visualizing the data. So with this thing, so what I try to say is what we can do with the data is that what we can do with this data is the first step is data visualization. And then next is what we get is exploratory data analysis. This is very quite interesting concept where it makes use of very basic statistical measures. Anything that you want to convey? Then I'm getting some prompts. Nothing, right? Can I continue or anything that is to be conveyed?
You can continue, sir.
Okay, right. So exploratory data analysis is very, very interesting concept where most of the budding researchers has to focus. Okay, that means mostly people who are having data science data science approach, machine learning approach, mostly they start working on modeling, they start testing the diagnostics of the model, and they do many things. But the basic crunch or a kind of a crux that lies is in these two. Whether you do modeling, whether you do a comparative analysis, whether you do any kind of a statistical techniques, before that you should do a data visualization and the exploratory data analysis. And then we can do some sort of a relational understanding, relationship patterns that we have just discussed. And now what we enter is modeling. Unless and until we know that there exists a good intensity of relation, we cannot see clearly that the model will be of a better fit or model will be of a good information. So now we enter that as into, there are very important modeling techniques, starting with, we say, a linear regression. Okay, and then how the model look like? Y is equal to beta naught plus beta 1 x, or I can write yi, beta naught plus beta 1 xi plus epsilon I equal to 1, 2, and so on, n observations. So now my dependent variable, I can write this as y is equal to function of x plus epsilon. This function of x is this, which will regress to my dependent variable. Okay, so my regression part, which takes beta naught cap plus beta 1 cap xi, gives me an amount of information about y. So here y is continuous, and the models of where y is continuous and with a set of combination of continuous and categorical, where we use this linear regression. Now there are many instances where we come across different kind of regressions where my model has a similar structure, but my y takes yes or no, presence or absence, like disease presence and disease absence, live or dead, like this binary or multinomial. So such kind of a models is what we call like a classification models, like logistic regression, discriminant analysis, and many other techniques that we have in the term of supervised learning techniques. And another set of model that we really one should know, again we can write in this fashion, but here now my y is count. Okay, it's a kind of a discrete setup functioned with a set of predictors. So such models that we get is count data regression models. Count data regression models, very predominant one is Poisson regression and negative binomial regression. So what I'm trying to convey here is, when we talk about regression analysis, it's not just only linear regression or a kind of a simple linear regression or multiple linear regression. We have a basket of regression models which are defined for various purposes. One is a classification model, bringing out a classification rule for separation and allocation. One is estimating the count using set of predictors. The other one is estimating or predicting some sort of information using the things. So basing on the context, the choice of the regression model do vary. Now we will confine, as it was discussed, we will confine our discussion to simple linear regression and multiple linear regression. Okay, so when we have a two variable model like beta naught plus beta 1 x plus epsilon, where one variable is independent variable or regressor or a kind of explanatory variable and y is a regressand or dependent variable, then this is the very basic model where we work on various things to estimate, to obtain the OLS estimates of beta naught and beta 1, and then to see whether the model fit is correct or model adequacy is correct or not. In fitting the any type of simple regression or multiple regression, we generally look into two important aspects. One is model adequacy and the other one is model fit. So generally model fit talks about mean square error of the model, and then adequacy is about R square. Okay, so there are important measures or a kind of indices that helps us to understand how far the independent variable is explaining the percentage of variation or percentage of variance about the dependent variable. Now, when we take a model like this, y is equal to beta naught plus beta 1 x plus epsilon, it has certain assumptions. It has certain assumption. I'm not getting much into the mathematical part because it's a kind of a mixed group, I understand. Okay. Now, generally what we look for is like a linearity in model parameters, assumption of homoscedasticity, where uniform variance is spread across the model. Third one is existence assumption. That means y is distributed with normal with mean y given x and sigma square y given x in a graphical way that we can say. And we can go with errors are normally distributed. Now, when I talk about existence, let me take the graph like this. That is, let us take income on x-axis and expenditure on, I'm taking a common example that we can make out. That now let us take income, let us take 1,000 per week, 1,500, 2,000 and 2,500 like this. And expenditure we can start with 500 1000, 1500, and 2000. Now, how that existence comes is, there will be a set of individuals in a particular households or a particular community where we do this survey, that there will be a set of households whose income is 1000, but at the same time their expenditure level do vary. So I can get a cluster of points like this. And similarly, 1500 income group and their expenditure, and then 2000 and their expenditure, and 2500 and their expenditure. Now in all these things, I can easily derive the centroid value, and the distribution of this will give me the spread of the data. Something like this. Now, when we have this kind of a thing, that means mean mu y given x is equal to x exists. Okay, so that is how we talk about the assumption of existence. In the model. Linearity in model parameters, that is beta 1 and beta 2, beta naught and beta 1 are degree with unity, and homoscedastic with respect to expectation of the residual square is equal to sigma square, and the assumption of normality. Now we'll move to a data set, and then we'll come back to the multiple regression. Again, we'll take some preliminary discussion on the assumptions, where some additional assumptions are available for multiple regression, like multi-collinearity. Okay, that we'll be discussing later. Right now, we'll just take the data set. I'll be using a very simple data set. This is the data set that I'm trying to use. That is age of the sparrow in days and wing length in centimeters. Okay, age of the sparrow in days, and then wing length in centimeters, that we can see this. And this is the data I'm trying to use now. Very simple model. Let us try to start constructing that. And now, first thing is loading the data with the background notion that you are well aware of R. Generally, this is one of the method that we import the data set in R, that is CSV files. Similarly, we can do XLSX files, general Excel workbooks, and then DAT file, text file, SPSS files, SAS files with the prefix term as read dot. This is a very basic version which doesn't require any kind of a package. Just like that, we can import the data. Now, the text within the parenthesis of read.cxv is what we call arguments. The first argument is about the data set name. That is, from where the data is to be chosen. This file path can be given, or instead of that, just like that, we can choose file.choose, and then instead of path, when we use file.choose, automatically a wizard will get generated. From there, you can go to the location and then choose the required file for necessary execution. And now the next argument says header is equal to true. That is about the labels that we have in the first row of the data set. And I generally suggest to take this function attach, and the data is temporarily stored in CR, and then attach CR means whatever the variables that are available in this particular data, they can be called directly without using that dollar.
मेरा ही साउंड कहाँ गया क्या?
Hello?
So you can continue.
Yeah. So directly we can make use of the variable name that are already available in the data set without using the call symbol, that is dollar symbol. Now, as I told you, the first thing that we do is presenting the data in a graphical way, where I use a simple command plot with the basic arguments. One is on x-axis and the other one is on y-axis. And then we can extend that to beautify the particular graph. We can extend further, like adding some more arguments, label on x-axis, label on y-axis, the title that we can generate or that we can use for defining the plot. Okay, now so right now we have 1, 2, 3, 4, 5 arguments. So this x lab will give me the label on x-axis, y lab will give me the label on y-axis, and the main argument will help us to define the main heading of the graph. Okay, and then scatter.smooth is another command that we use to define a smooth line about this particular graph. Once this data visualization is done, we'll come to know that how the tendency of the data points is moving. That means as the number of, this is quite trivial to understand, that as we increase, as the age increases, gradually the physical anthropometric parameters will gradually increase, okay, to some extent of age level. But still, now when I come to know that this is the wing length of the sparrow, I can easily, I can make out, or I need to predict to what age or what is the age of that particular sparrow. So wing length can be measured easily, and then, but age is a question mark. So we use wing length as x-axis, independent variable, and then age is to be predicted. In that way we can go, or given age, what set of a wing length that we can generate is also can be done. Now, once the data visualization is done, we go with correlation analysis, where I am storing the data in Corel using a cor function of the data. I'm just restricting the decimals using the round function. Okay, and then there is a test statistic to test the significance of the correlation. That is in a formula wise, we do like this: rho is equal to 0, h naught rho equal to 0 against h1 rho not equal to 0. The test statistic that we get is r into square root of n minus 2 by square root of 1 minus r distributed as t n minus 2 degrees of freedom. So this is the test statistic that we use for testing the significance of correlation. Okay. Now that can be done like this, and then fitting of the model. Once we know the relation and its testing is done, now the fitting of the model is done with the function called LM, linear model, where the dependent variable and independent variable, and the second argument contains the data. Data argument should give this where the data is stored, that variable where the data is stored. Okay, after that it can be stored in another temporary variable like SR, just a name that I have given that doesn't have any clear-cut meaning, just a temporary variable to store the final model. And here summary of the standard, this outcome will give us the total R square, ANOVA structure, significance of beta naught and beta 1, significance of regression, many other things. Now what we do is we start working on these things and then see the discussion on interpreting the outcome. So I take you to the R. Just to save the time, I have already made ready the the code, so that I can spend more time on discussion and interaction. Now let us load the data. I have already explained this particular data, and then now the data is loaded here, age and wing length. Now attach function, plot of this, and then smooth line. So when you see this, this is the distribution of the spread of the data, that this is the age and then wing length and then sparrow data, the title. So more or less the data points are well connected with the smooth curve, and slight deviations are there. The deviation that we see in the next graph also. So here I use another additional ggplot function. The model, I need to run the model for that. No, this is not required. This is for some other purpose, sorry. Okay, now, correlation. And then the correlation test. What is the correlation now for us? Correl is 0.987. So the correlation between age and wing length is close to 0.987. High intensity of positive correlation that can be made out with respect to the direction of the data, the tendency of the data, that increasing in age in days, gradually the wing length will also have a gradual increase in the wing length. That means there will be growth in the physical structure of the sparrow. And then test for correlation. So we can see here that the Pearson product moment correlation is executed with the statistic value as 20.027 and 13 observations. As I told, it is n-2, so degrees of freedom is 11. And then p-value is 0.0000 and many 0.000 at the 9th decimal you have this. So it's taking almost close, at least p-value, it indicates a significant thing. What does significant stands here? That the correlation is not close to 0. It has some weightage that can explain the degree of intensity between the variables that we have chosen. Now let us run the model. And this model is this. It is I have indicated that y cap is equal to 0.7131 plus 0.2702 into wing length. Okay. Sorry, age. I wrongly typed this one as age. Or I can do one thing. Yeah. Age. And the summary is this. Where it starts is it will talk about the median of the residuals and the minimum residual and maximum residual with the quantiles of that. So I think more or less symmetrically distributed. The errors are symmetrically distributed. Okay, median close to 0. Okay, and then the t-value for test for beta 1, t-value for test for beta 1 is this. So it's significant. So beta 1 is not close to 0. It has a weightage that can contribute in predicting the wing length of the data. I'll do one thing. Rather doing this, let me revert this age to be predicted, because physically we can see the wing length. So let us do this. Now a slight change has come. Okay, means how does this look like? So now the estimated wing length beta 1 cap is 3.601, and then standardized t-value is 20.07, and the significance is there. So the coefficient that we got here, 3.601, this is just for experimentation I did. We can revert back to the actual thing where we can do this wing length and age. Okay. Now, yeah, beta 1 and beta naught both are not equal to 0. That means it has some influence of the regressor variable and its coefficient is there in understanding the wing length of the birds. And at the same time, there is some constant effect that the average wing length will be 0.717 centimeters at the time of the birth. On an average, the wing length will be 0.71 centimeters. And now 1 day, 2 day, 3rd day, 4th day, when we just substitute the number of the wing lengths, that interpretation will come. And then R square value is 97. It's simple that I can do like car test square, square of that correlation, coral. Square of the coral is nothing but your R square value. In an analytical way, you can see 0.974. Okay, so it says that whatever the simple correlation value that we get, the square value of that particular directly we can take it as a coefficient of determination, which is nothing but your model adequacy. Now, the percentage of variance explained, the wing length is about the model is 97.4. So better prediction we get, and then we can create a model like this and creating an absolute line. This is how we can generate the data, generate the graphs. Now, once the model is ready, I can use that model for prediction of newer observations like this. To do so, in order to predict the wing length, I need to give some data sets, data points of age and as a data frame. How we define a variable, a numerical variable in R is C of the subsequent values separated by comma, and this data dot frame will create a structure so that directly it will take that value and substitute in the model. Now, this function predict is a function that helps us to get the predicted values for a given value of new x values, that is 19, 22 and 24. Clear? And then now what we have to do is predict new is equal to predict of the model. SR is the model, and new data, where the new data is stored, it is in age underscore new variable. Okay, so this prid underscore new will contain the 3 new predicted variables for the 3 new given x values. Now we can club those 2 different data frames into one particular thing as using the function called cbind age new and pred new. And then we can name that as the new observations, names of new observations as this. And then, okay, let us do this and then slowly understand. The spread new will contain the predicted values of that. And new observations is this. Okay, the meaning that we get of cbind is this. For given this, we got this. Now, names of that new observation, and then okay, I mean that will get stored there. Instead of predicted new, we get a new length. And then already we have around 13 observation. Now these 3 observations are to be added or appended below to that particular existing 13 observations. Now for which we use another function called row bind. Okay, row bind of data.frame of CR and data.frame of new observations. Now if I type new observations here, that name got changed from pred new to age and wing length. Okay, sorry, here instead of names I should have used new observation. Now this fit data will contain both the observed values and predicted values. Okay, let us run that and fit data. So now earlier there were 13 observations and then these 3 records are added. Now when I directly write this or export this particular data, we get this first column values also. To overcome that, to nullify that, we have to use another function called row.names of fit data is equal to null. Now you can see, even though it shows the serial number, but it won't get exported or it won't get listed when we export that into a Excel file. Okay, how do we export that? Using write.csv, given a path where to save and what is the file name. And then we have to use row.names is equal to false. So using these set of arguments, we can directly export the file into CSV in the required location. Okay. Now the first argument is that what is the file that is to be exported, and then second one is the path where it is to be exported, and the third argument is about the row.names is equal to false. Now once I do that, now in the preferred location I have this. You can see this is the current latest one. Now I have the data exported directly along with the existing information that I have used for fitting the model. So like this is very basic elementary one that we use for understanding the relation as well as building the model between a set of variables. Fine. Now the similar kind of a set of codes can be used for different data sets, like I have shown here that sleep duration sleep duration, I can take this as a independent variable, and I can predict how much will be the quality of sleep, or having higher stress level, how much quality of sleep will get affected, or higher heart rate, is that related to higher stress level, and so on and so forth. Like this, we can do many other what do you say, this experimentations with the data set. Okay, now we'll move on to the multiple regression, wherein I'll show the set of R codes first, and then we'll move further. What I'll do is, as of now, are you able to follow, or are you able to understand what I'm trying to convey, and then figure out the total conceptual view of the regression? As of now, any queries that you have? Yeah.
Very good evening, sir.
Good evening.
So I need to ask, in your notes when you are writing in Word file, there one word is you write it is LSL. What is that meaning? I am missing out that thing. I am writing that time and I miss.
One second. Let me take that. Where? This one?
Yes, sir. Little bit up, sir. Little bit up. Sir, that discriminate analysis you were saying now, if our data is binary, then we can go for, yes, sir.
Yeah, this is nothing but supervised learning models. SL, you want to know this?
Okay, supervised learning models. Okay,
Yeah, supervised learning models. Because we have in machine learning, we say the regression analysis is renamed, or a kind of a different notion, that predictive modeling or a predictive analytics. Okay, like
yes,
that, we have machine learning algorithm like logistic regression for binary and multinomial setup. Support vector machines are there, artificial neural network, logistic regression, this discriminant analysis, okay, ROC curve analysis, and then you have decision trees. Like this, there are many supervised learning techniques for that particular classification model, okay, for building a classification model.
Okay, so one more doubt I have. Maybe it is silly, but I need to ask. If we import a simple Excel file compared to CSV file, means what is the major differences between CSV file and Excel file? Is in the interpretation they make any differences if we do work with simple Excel file? Is there any differences if we do work with CSV file in R?
See, the thing is, there is no much difference in these two different formats are importing the data into our environment. Okay, there is no mandatory that you should only work with CSV or you should only work with XLS files. Now, these are all the different ways that you can, that allows you to load the data into R. That is one thing. Second thing is, there is no influence or change in the interpretation. Okay, it's just a loading process. It's just a loading process of data into our environment. And when we come across the CSV file, is nothing but when you open the CSV file, it will look like a columns only, but actually it looked like this. I can show you that. One second. Yeah, this is a view of a CSV file, separated comma, separated value. Each value is separated by a comma. Okay.
Okay, sir.
Okay, but now there is a function called read library XLSX. When you have multiple data sets stored in one particular Excel workbook and you want to use directly that one, then you use that function called read library read Excel, and at the last argument, like how you do here, like here, what we did, we used header equal to true, right? Now, if I change this as read Excel SX.
Dot XLS. Yes, sir. This thing I know, sir. Just
Yeah.
I want to. Sir, results में तो is not get affected, no?
No. Here one more thing is that we have to give sheet equal to 2.
Okay,
Which
sir.
sheet you want to import, okay? Or sheet equal to a double quotation regression data, okay? If you give like this, then automatically that particular sheet will be taken and loaded into the R environment. Yeah, you are about
Thank
to
you,
ask
sir.
one.
Thank you very much. Thank you, sir.
Any other?
Sir, good evening, sir. So my
Good evening.
question is like, during when we discuss about the single, like simple linear regression, we have talked about the model accuracy and a model fit. In that, we talk about the R square and mean square error. Can you tell us like more about that R square and mean square error, what it interpret and how we will understand from that?
Okay, good. Now let me explain that using this graph. First thing is model fit. Okay, as I told, that depends upon the mean square error. Now, how come mean square error will get computed? It is nothing but the sum of the deviations from this point to the fitted line. So, this is the error value 1. This is error value 2, negative deviation, positive deviation, again slightly small deviation. When we take these deviations and aggregate it, we get the value of mean square error. Now, whenever we have a least mean square error value, that means that model is of a good fit. Now, the question is, when the model is of a good fit, means like this. This is one example. A typical example here is that whenever the fitted line is will connect majority of the data points, giving out a smaller deviations from the observed value to the fitted value. So when the deviations from the observed value to the fitted line is quite smaller, then automatically model is able to give a true prediction about the dependent variable. Then in such cases, the mean square error will be quite smaller. Okay, now let me show you another example of this. 1 second. Let us take this particular data, like sleep duration, and let us take some randomly. I take this heart rate and what do you say, any variable like physical activity and heart rate. Let us take these two variables to show you another view of the thing. I can fit data in Excel also. We can do that. Data, sorry, insert graph, this, sorry, data of this, where physical activity and heart rate is taken. This is stable, quite stable. This is another example. When you see this, there is no trend observed here. Let us change the axis. Let us make it 50. Right. Now, this is one best example. Coincidentally, we got that increasing the physical activity, there is no proper trend observed in the heart rate. So this kind of a models that we get is known as just an intercept model. There is no slope. There is no slope like this, or there is no slope observed like this. This is completely uniform. This is completely uniform. So this is a no slope model. And the mean square error, let us suppose do that also. For this kind of a thing, right click, add trend line, okay, where I create display equation on chart, display R square value on chart. Say this. R square value is too low. That means there is no relation between the physical activity and heart rate. That means increasing physical activity that does not relate to increasing of the heart rate in this particular example. Okay, and now R square is too low, indicating that that doesn't contribute much to talk about heart rate. So model is not that adequate enough to predict the heart rate using the information of physical activity. Okay.
Or so we can say R square basically tell about the relationship between two variables.
Two variables. No, R will tell the relationship between two variables.
Okay.
R square will tell the adequacy of the model, to what extent it can help us to predict the Y.
Okay. Sir.
Okay. Now let us see this even in data analysis. Okay, data. I think I didn't do this yet. Let me. Okay, fine. So like this, you have different scenarios where you get close data points to the fitted line. And if you see in the example here, there are many data points which are farther from the fitted line, isn't it? Then automatically mean square error will be at a larger value. That indicates that's not a good fit. Model cannot be relied on. Right?
Okay.
Yeah.
Hello.
Yes.
Good evening, sir.
Good evening.
I want to ask you one question is related to linearity of two variables. Whenever we fit a simple linear regression model, that two variables y and x are must be linear. So how to check linearity of that two variables?
Using normality test you can do.
Normality and
normality means
can you
generally
conclude that by using a
the
scatter plot?
linearity can be observed. The linearity can be observed. Very best simple thing is to have a scatter plot between. I mean, you want to see the trend is linear or not, or what?
Yeah.
The trend is linear or not. Then, in order to see the trend in linear way or not, then you can use a scatter plot.
Yeah. Okay, sir.
Yeah.
Thank you, sir.
Yeah. So, can we move to multiple regression? And then we'll take the discussion.
So before that, there is a question in the chat box saying if there is no linear relationship between dependent and independent quantitative variables, then what is the solution?
Okay, then we'll go with the fitting of nonlinear regression. We'll see the structure, how it is, whether there is a increasing x, there is increasing y, and then at a static level, it is coming stabilizing and then coming down, or a curvilinear approach. What sort of a behavior? That's what another madam also asked, that to see the linearity between the pair of variables, I mean trend, whether it is observed or not. When we get a scatter plot, basing on the shape of the scatter plot, we can decide whether to go with a linear or a non-linear structure. If it is a non-linear structure, I can show here, as we did here, no? Right click, add trend lines. I mean, for example, I'm trying to tell, just to clear the doubt. So like this, if you get a different patterns like this, or a polynomial, or a power, or a different moving average, then we can choose that exponential fitting or a nonlinear fitting, okay, or a quadratic. All these are nonlinear fit, a logarithmic fit, or a polynomial, second degree polynomial, or a cubic polynomial. Like that, we can use a particular nonlinear pattern and then get the model, right? Shall we proceed further to multiple regression?
Excuse me, sir. Last question, mine.
Yeah.
Sir, the one term is oftenly be used despite of R square, that is pseudo R square. Sir, what is exactly pseudo R square?
Pseudo R square mostly is not that meaningful or useful in the simple regression setup. Okay, and then when it comes to multiple regression, also we mostly rely on adjusted R square than the R square. That I'll take it in the further discussion, right? Yeah. Now, let me take another data set. So this is another data set that we take for understanding the multiple linear regression. So these are all the variable names, and there are around 33 records. And now this is the data set of anthropometric data. SH, the first column stands for standing height in centimeters. This is sitting height. Sitting height is nothing but from the waist to the shoulder. How we sit in erect way, then they measure that particular height. And the third one is upper arm. Okay, so UA is upper arm, and then FA is forearm. This is H is hand, upper leg, lower leg, and foot length. Okay, now we have to use this data. Sorry, you have to use this data to model and now here directly I'm trying to tell to save the time and so that I can give more time for discussion. Here my dependent variable that is to be predicted is standing height. So given a sitting height, upper arm, forearm, hand, upper leg, and lower leg, and foot length, to what extent I can predict, or to what extent I can give information about the standing height. Okay, so we will take this data and then start working on the things. One second. Yeah, so here I'll be using, since the total data structure will become a matrix, so we'll be using a basic inbuilt library called mass, and OLSRR is another function, ordinary least square. This is used for doing a stepwise regression, I mean variable selection procedure. And then the another package that I use is ggcorplot to create a nice structure of correlation analysis. And then as usually, these are all the basic things that that we can make use of. And then just a basic recall is that this is the way that we do install the package. Mostly you can do directly from RStudio and then call that library. Here itself the change is there. Okay, this is the common as such that what we have done in simple regression. Use the correlation function and then the data set where it is loaded and squared, I mean rounded with the 2 decimals, and that is stored in that. Now another function that we use here instead of testing of significance, another function that we use here is correlation car_pmat to get the p-values of each pair of correlation that is constructed in this particular MLR data. So this p.mat contains the p-values that are associated with each pair of independent variables and independent and dependent variables. Okay, now where the difference is, in the simple linear regression, we used car.test, but when it is the dimensionality increases, directly we can use this function called car_pmat, so that it will contain all the significant and insignificant p-values of each pair of dependent with the independent and among independent variables. Okay. Now, this is a function which gives us the car plot with the different color textures. Okay. Okay. Now, what we'll do is we'll start with this, and then once we execute, I can show the changes how it comes. Let us come to this R. We close many files. Okay, now let us start as I'm doing one by one step. Library mass, OLSRR, and then GG card plot. Done. Now the data set is loaded. Then this is not required. Head.mlr is nothing but it will display the first 6 records, and then attach MLR and then plot MLR. The basic plot does this. Now let me do one more thing. This is quite clumsy to just explain. I'll take one subset of this and then we'll redo this. How we can do is MLR rows, and then we can take one C of 1 comma 1 2 1 2 3 4 5 1 comma 5 comma 5 4 to 6, right? So just I condensed the graph. Instead of taking all variables, just I have chosen a pair of graph. Now you see this. I can increase the dimension. Let us try to increase the things. Now, if you see this, this is called matrix scatter plot, wherein this is one scatter plot between forearm and standing height. This scatter plot is between hand and standing height, and this scatter plot is from upper leg and standing height. And these three are between hand and forearm, forearm and upper leg, hand and upper leg. Here, 2 points are to be noted. One is, whenever you build a model, the first thing that we see is how far each independent variable is linearly connected to the dependent variable. Why I'm using linearly connected? If the trend is very nicely projected, that is increasing values of one particular variable or decreasing values of one particular independent variable is giving an increasing or decreasing trend in dependent variable, then I can easily figure out that a unit change in independent variable, how far the influence will be there in the dependent variable. This is the interest that lies whenever we are trying to build a model, that mostly the independent variables should be highly related or highly the degree of intensity between a set of independent variables should be highly related with the dependent variable. That is the interest, that is the expectation that we look for. But what it should not be is that the same degree of relationship should not be high among the independent variables. Like here, if you see hand and forearm, there is a slight degree of trend that is noticed here. Okay, and I can take out a complete plot now like this. If you see here, this is one particular plot between hand and upper leg, slightly have a trend, but whereas this lower leg and upper arm has some sort of a trend again, whereas the foot is completely scattered. This is a scattered plot. It shows that very weak relation between sitting height and lower leg. And at the same time, upper leg is completely weakly correlated with the sitting height. So in general, sitting height doesn't have much relation with any of the other independent variables. So this is what is required when we run a multiple linear regression model. Now why I'm saying so is that whenever a pair of independent variables or a set of independent variables are highly correlated, that will lead to the issue of collinearity in the multiple linear regression model. So we should wish that none of the variables or most of the variables of the independent variable should not be highly correlated among themselves. Now the question comes, what happens if there is a collinearity or a kind of a multicollinearity exists in the data? That will create data redundancy. That will increase, or statistically we can say that will inflate or that will overestimate the regression coefficients. Another statistical rationality is that the confidence interval will not be reliable. It will get a wider confidence interval. The statistical properties of like unbiasedness and then minimum variance may not be met. When they are not meeting these properties, the model that we get may not be of a reliable model, and that cannot be taken for granted. So what we can do is that in the graphical plot itself, mostly we can counter whether they are correlated to the extent or not. But one thing that we have to observe is the first row. The first row should be having a better amount of degree of intensity. Now, just let us spend a couple of minutes in the same graph. When I take, let me take 1, 2, 3, 4 variables and then separately 5, 6, 7. Okay. Let us redo that. 1, 2, 4. Now see, this is my dependent variable and these three are independent variables. So these three are scattered up. Among the independent variables, these are weakly correlated. So I'm not worried about the collinearity issue. But at the same time, I should look at how far the sitting height is having a trend with standing height, upper arm with the standing height, and forearm with the standing height. Slightly scattered, but not as that here. So there is some sort of a relation that exists between the sitting height, upper arm, and forearm with standing height. Now let us redo this by taking the last 5, 6, 7. CO, or I can say 5 to 7. Or 6 and 7, let us take. Now standing height with the upper leg, standing height with the lower leg. So they have a better trend. That means what we are trying to do in anthropometric way, a person who has a longer length of upper leg that means from the waist to the knee, and a longer lower leg from knee to the ankle, there is a high likelihood that their standing height is high. Okay, a gradual increase in the upper leg can easily say that the person standing height is higher. Now there is one issue here. Upper leg and lower leg are having a little trend here. Okay, now that can be ruled out because we are not sure that all the variables are quite important in the model. Once we do the variable selection, we can easily make out that what are the important variables and whether having a scatter plot of those variables will give still the trend of linearity among the x's. Right? Now, let us do a GG chord plot. 1 second. Run this. Let us first compute the correlation. Now you want to see the correlation? Let me take those correlations. Yeah, standing height is highly correlated with sitting height, and then upper leg and lower leg. See, lower leg is highly correlated with standing height than upper leg. So like this, we can understand the relations basing on the higher values of the correlation values. And coincidentally, here all the correlations are positively related because if you see this, all the relations are in an increasing trend. So there are no relation of negative. Okay, obvious. It is so quite obvious that when you measure the gradual increase of the body measurements over the age, then if increase in one foot length or increase in the inch of the foot length, increasing in the height of the ankle from the knee or increase in the knee from the waist, automatically there is a gradual inclination of height in the total body structure. So this kind of a data set, mostly we cannot see the negative correlation. And let us compute the p-values. See here, the significant p-values are observed from sitting height and standing height, and insignificant is between upper arm and sitting height. So that means the scatterness which is observed between upper arm and sitting height cannot figure out there is a trend observed between these two variables. So like this, wherever the value is less than or close to 0.05, such p-values we can take that the correlation is quite closer to 0, absence of correlation. Now, as I was telling that the first row with the standing height with the dependent variable, all the correlations are significant. That means each and every independent variable do have some sort of a contribution to speak about or to explain the variation in the standing height. Okay. Now let us continue that with a graphical notion. GG chord plot. So this is the GG chord plot. Now let us redefine that with the different methods. This is the circle, and I can nullify the lower using the argument type lower, and then label is equal to true, and method is circle. Label is equal to true means it will display the values. Okay, since this is a square matrix, I can just display only the one particular part. And now if you see, basing on the intensity of correlation, the circle takes the shape. Larger correlation, dark color, and then larger circle. If you see, this is a weak correlation, there's completely white and a smaller circle. So this is one typical a slighter advantage in presenting the data and interpreting the data. It is self-explanatory that basing on the correlation value, the color and the size of the circle, intensity of the color and size of the circle do vary. Now, we are adding one more argument in this particular GG curve plot, that is the P dot mat. That is, when we take that particular value, now what is the difference that we noticed? Can you see that? In the previous graph and this graph, you are noticing a cross mark. So these cross marked indicates that they are all insignificant correlations. So all the independent variables with the standing height are having significant correlations, and the highest is with respect to lower leg, and next is with the forearm, and then you have sitting height. Now let us start doing the fitting the model. The function again here, what we use is the same function lm, but only slight change is that first we have to write the independent variable, and then right side argument either you have to do like sitting height plus upper arm plus forearm plus upper leg plus lower leg. Instead of typing all these things and create some sort of an error in the coding, just use a dot argument and it will automatically take all the rest of the variables. It will treat all the rest of the variables as independent variables and it will take from data MLR. Okay, now let us run that. So this is the model that we write. Standard is constant is 17.1487 with a sitting height of 0.183 is the coefficient, minus 0.24 upper arm plus 0.38 forearm, and likewise you can take the model. Now let us go further with the summary. Again, median residual is quite closer to 0. So errors are symmetrically distributed with the range. If you see the minimum and maximum of the residual, it is quite uniform. So homoscedastic assumption is also satisfied. And then, this is the significance of each regression coefficient that is tested. So with the full model, this is the complete model. With the full model, we understood that the significant variables that can be treated as sitting height and lower leg. That means the posture from the waist to the shoulder and the length from the knee to the ankle. This is the information that we get from the full model, but that is not the final model. Okay. Now R square is 0.89. So with all the 7 variables, around 89.23% of information about the standing height can be made out. Right? And then the model is significant. This is the F statistic, and this is the degrees of freedom for testing the significance of the regression model that we have got. It is quite significant. That means the information that we get here, sorry, let me give that like this. The equation, using this equation, we can easily predict the standing height up to 89% or close to 90%. Information will be accurate in predicting the standing height. Now let us run the ANOVA for the model. which talks about the residual sum of squares is also too low. That means model should be of a better fit. Now, the question comes that do I need to consider all the models, all the variables in the data, or do I get a best subset out of the data, right? So what we do here is we use a function called step AIC, that is Akaike information criteria, with which it will help us to understand the good contributor or a bad contributor, that is what sort of variables that are relevant in the model, that those will be kept in the model. Now here in the direction we have three different methods. One is forward, the second one is backward, and the third one is stepwise. And in our coding, that stepwise is called both. So stepwise algorithm is a combination of both backward and forward. Okay, so we use this. Now I'll take this data into Word document so that I can show there and explain one by one. Let us start this way. Now this is the approach. It will go like this. It will start with all the variables in the model, that is a backward elimination, and of these, which one has the least AIC? Okay, the selection of variable happens using the AIC value. The variable with the least AIC will be eliminated first. So among all the 7 variables, upper arm has a least AIC, so that will get eliminated from the model. So in the second iteration, if you see that upper arm is not there. Now the model will go with the forward elimination, wherein again the same criterion with the least AIC will be eliminated from the model. So now the least AIC is with upper leg. In the next iteration, that upper leg is not there and upper arm is not there. Likewise, in the iterative process, the variable with the least AIC will get eliminated in the iterative procedure. Now the question comes, when to stop, right? When to stop? If you see, there is another condition that we need to look for, is that the overall model AIC is 46.22 and the least AIC, the variables whose value AIC value is least is 45.02. Clear? Now model AIC is higher than the least AIC of any variable, hence there is a requirement of another iteration, right? In the second iteration, overall model AIC is 45.03, but the variable's least AIC is 43.55. So then continue the iteration. Now the overall model AIC in the third iteration is 43.56, and the AIC of the least AIC of this particular variable is 42.19. So again, there is a requirement of another iteration. Now if you look here, the model AIC is 42.2 and the constants AIC is 42.2. Now the iteration terminates. So whenever the model AIC is close to the least ASC of the existing model, then there is a termination process that happens, and what are the variables that we get in the last iteration, that will alone be the final model that we account for. So the final model has 4 variables instead of 7 variables. That means the amount of information about the standing height can easily be explained with only 4 variables rather than 7. Now, what are the 4 variables that I need to take hereafter? Sitting height, posture, hand length, lower leg length, and foot length. Generally, there is a tendency we do here, right? A person whose foot length is larger, there is a high chance that likelihood that their height will be at a larger value. Hand length, right? There is one Sanskrit word that ajanubahu means larger hands. They will have a longer posture, height posture. Clear? Like this, instead of 7 variables, now I can easily talk about standing height with only few. That reduces my time, the labor, that is that I have to time investment. I can just talk about 4, get the data about 4, and then I can easily predict standing height. Now, the question comes, I'm very much happy that the reduction of dimension happened, right? Now, what is my model R square? What is the model mean square error? How does the scatter plot look like? These 3 questions is the point that we look for now. So for which we'll go back to the model. Now, what are the variables we have? We have standing height, hand, lower leg, and foot length. Sorry, sitting height. Now, let us consider those variables. The position of those variables are 1, 2, 3, 4, 5, and 6. So now let us confine the data MLR, with 1, 4, 2, 2, C of 4, 2, 2, 4, 2, 6. Okay, then we have to insert 1, C of, no, 1 second, there is one more parenthesis that is to be done. Yeah. So now, what is there? It should not come. Sitting height, hand, lower leg has come. So there is a change in that. So sitting height is correct. Lower leg should come. Lower leg is what position? Lower leg. Sitting height is 2. Hand is 3, 4, 5. And lower leg is 7. And forearm is 8. Okay. So C of 2, 5, 7, 8. Yeah. So this is my scatter plot of the final model. So most of the independent variables are scattered among themselves. Most of the independent variables do not have much relation. So there is no issue for me. Now I can run that model. Summary. If I get the summary, then I'll be getting the total information. Okay. So all the variables are significant, and then residual standard error is too low. R square value is 0.88. Earlier with the full model, R square is 0.89. With the 7 variables, R square is 0.89. With 4 variables, R square is 0.88. R square is 0.8. There is no much difference, loss of information, but still we sustained or we retained the complete information with just the 4 variables. That means that the remaining 3 variables do not contribute much in understanding or predicting the standing height. Okay, so yes, anything? Now I'll give time for discussion. I'm about to complete that. Then we can take time for discussion, right? Now, look at this. The total significance of the regression is also quite interesting, that the model is adequate enough. R square is high. 88% of information about the standing height can be extracted or can be spoken with the sitting height, hand, lower leg, and foot length. It makes sense logically also. When we look in a general context, in a statistical perspective, using some algorithm, that algorithm doesn't know the physical characteristics of these variables. However, whatever the logical knowledge, what we have about the physical characteristics, like higher the sitting posture, the length will be high, standing height will be high. Higher the hand length, the standing height will be larger. So we can easily make out that in a physical sense, that people who have a shorter hand will have a shorter height, will have a long hand, will have a high long posture, like this. So the statistical perception and the physical perception is coinciding very interestingly. And then with the 4 variables alone, we can easily predict the standing height with less error information. Okay. Now, as usual, I use this data structure to predict the new standing heights for a given record values of sitting height, hand, lower leg, and foot length. So these are all the different 3 records, 3 sitting heights, 3 hands, 3 measurements of hand, 3 measurements of lower leg, and 3 measurements of foot length. So let me run this and predict and predict. Okay. So this is the for different measurements of sitting height, like for 93.5, 22 point. How we can do this? Let me take this coefficient. What are the coefficients? 17.7654 plus 0.8481 sitting height plus 0.9049 hand plus 1.2886 lower leg plus 0.8464 foot. Okay. Now I can say that how I can compute 17.7654 plus 0.8481 into 93 point, the first record, plus 0.9049 into 22.4 plus 1.2886 into 39.1 plus 0.8464 into 7.1. This is how we get the the values. There's slight difference in the 3rd decimal and 4th decimal because I restricted my coefficient to 4 decimals. When the actual model takes, there will be multiple decimals there, but we can see this is how the prediction comes. Now, if I change the another value, I get another prediction. So this is how the prediction of the model, adequacy of the model, fit of the model does happen along with the various correlation factors. Okay. So now I do one thing. I'll take these last 10 minutes for discussion. Okay. Now the floor is open for discussion.
Hello.
Yeah.
Sir, I want to ask one question.
Yeah.
In forward and backward elimination, is it possible that from forward selection method and backward elimination method, we get same model for the data, same data set?
Mostly it is not applicable for all data sets. Okay. I can show that how it works for this data set. I cannot give a generic answer that it won't work or it will give the same result, but most often there will be a slight change. Let us see that. I can do this instead of both. I can use forward. Sorry. So now when you use this, sorry. Initial model and final model is the same. Okay, here for this particular data set, forward has given a different result and both has given a different result, isn't it? Now go with the backward approach. Now backward approach and both stepwise approach is same. Sitting, height, hand, lower leg and things. So it has given the same amount of information what the stepwise algorithm does this, right? So in general, we cannot say that all the three methods will give the same answer. Only for particular data set we may get. That is very rare. Okay.
But in that case, which model should we prefer?
We need to use stepwise algorithm because that is a combination of both forward and backward, and that is more robust. It is sensitive. I mean, it is more robust algorithm.
But can we take decision related to that model on the basis of R square?
No, that's what I told. No, once we completed the stepwise algorithm, we will come to know the final subset of best subset of variables. Okay, and then we have to take the R square of the final model.
Okay.
Yeah.
If R square of final model is small, then R square of means R square of final stepwise model is small, then R square of forward selection method. Then that situation also we should prefer.
I got your point. You want to run three models. You want to see where the R square is high, but R square is not alone the metric to decide the model fit.
Yes.
Okay. You have to look into the R square will just tell about the adequacy of the model, but you have to rely on model fit also. That is mean square error.
Mean square, or sometimes we can take a decision by using Mallo's CP statistic, or
yeah, that also. I have not covered many other things here. Okay. Yeah.
Thank you, sir.
Yeah.
Sir.
Yeah.
So regarding the collinearity, we have used the correlation coefficients to assess whether their collinearity is there or not. So one thing is that to what level we can consider correlation coefficient is there. Sometimes even 0.2 correlation coefficient is also showing significant. So is it there is any limit at what level we should consider that there is no correlation or
correlation matrix is one of the method in understanding whether there exists collinearity or not. Okay.
Yeah.
But that is not always suggestible. We go with the variance inflation factor, that is VIF.
Yeah.
Okay. Any variable VIF exceeding 5 or 10, we say that that collinearity exists with that particular variable. Okay.
Sir, in various influence factor, in different literature, some says it should be if it is more than 5, or some say even if it is more than 3, we should consider collinearity. What should be the
No,
appropriate?
it should be more than 5. It should be more than 5. Most of the softwares do follow that more than 5.
Okay. And what about the this adjusted R square and R square, which one we should give importance?
Huh?
There is an adjusted R square is there, no? And another one is R square is there. So,
yes.
So which one we should give more importance?
We should use adjusted R square mostly.
Yeah.
Okay. Right. There is some question in the chat box also that if there is no linear relationship between the variables, then we go for non-linear. But given the linearity assumption should be met regression, and I didn't get this question clearly. Sorry. And then there is a continuation from the same person that while doing stepwise regression, you said that it reduces cost and time. But how come when they already spent? Okay. See, it's for the new records. Anyway, that we have covered, we have already invested some amount. When you want, once the model is ready, that model is useful for the new predictions, for the new entries. So now we can curtail the 7 metrics to only 4. So using 4, you can easily make the things workable there. If one independent variable is ordinal with the range of 1 to 5, then is it necessary dummy coding? You need to introduce a dummy. No. The thing is, dummy variable regression mostly comes with a categorical variable where, like, when you want to say this, we can introduce dummy variable also, provided when you want to see the adjusted factor of that particular category, how far it is influencing on the dependent variable. Okay. Right.
Excuse me, sir.
Yeah.
Hello.
Yeah, please.
Sir,
madam.
I need to ask first. Sir, in today's lecture, logistic regression is also there. You didn't cover that. I need to learn that thing. Okay, sir. Logistic regression.
No, I was told the regression, multiple linear regression and simple linear regression. That's why I planned so that I can go in detail slowly about these two concepts. Logistic regression is quite important in modeling aspect. That is one of the very robust technique in classification. Okay. You can do one thing. You can reach me out. I can just share some insights about logistic regression or what doubts I can clarify that you have about logistic regression.
Sure, sir.
Okay. Yeah.
Okay, sir. Sure. Thank you, sir. And one more question, sir. If our data is non-linear, means there is no linear relationship between my multiple data in dependent variable. Can I apply stepwise regression model to selection of variables, important variables?
There is another for non-linear regression methodology also. You have a similar kind of a stepwise algorithm where it will help us to identify the best subset. Okay, there is a separate methodology is available there. Yeah.
So can you name that?
Same stepwise algorithm only.
Okay. Thank you, sir.
Yeah. Hope I have reached to you with my presentation, and then any doubts you can reach me out to this email ID vvardhan.sta@foundry.ac.in.
Hello.
Yeah.
Sir, one more question, please. While fitting logistic regression model, can I ask question on logistic regression model?
Yeah, you can.
While fitting logistic regression model, if you have a response variable with multiple categories, means 0, 1, 2, 3, so or 1, 2, 3, 4, 5. So which can I fit that model on our software?
Yeah, our software is having program on multinomial regression, multinomial logistic regression, binary regression. All packages are available. Okay.
Okay. So I fit that model on our software also.
Yeah. Now
when categories binary response is not there, when multiple response is there,
No, yeah, that's what in programming, there is only one particular programming code, a single line of R code, where it will allow you to do for a binomial logistic regression or multinomial logistic regression.
Okay, sir. Okay. Thank you, sir.
So multiple regression will be used over simple regression when there are more than one independent variable. Okay, that's the question. I will share the R codes with the organizers with Dr. Shikhar. He will share with you. Okay.
Yes, sir. And related to ordinary logistic regression model also, we can fit, no?
Yeah, yeah. In our software, there are already established packages available. We can do all sorts of a multivariate analysis and all sorts of a classification models also. Okay.
Sir, I request you, please, if possible, can you share your code with us?
Which code?
Ordinary and multiple logistic regression model.
Yeah, you can mail me. I'll share the links. Okay.
Okay.
Yeah.
And
Okay,
one more thing, sir. If possible, if you can take one lecture, we have 8.
You can take lecture. I didn't get.
Sir, I'm saying if you can take, if it is possible for you to take time for a small lecture on logistic regression, multinomial logistic regression, how to do in R, so it is very helpful for us. If it is possible for you, sir.
I'm very much volunteer to share. I'm very much interested to disseminate the knowledge or whatever the knowledge I have, provided there is a slot according to the organizers. Okay, that is left to Dr. Shikhar. Okay.
No issue. Okay, sir. Thank you, sir. Thank
Yeah,
you.
yeah. Because I don't want to create, some kind of a discomfort environment to Dr. Shikhar. Okay.
Sir, definitely, we are going to cover it tomorrow. The logistic regression
Oh,
and
logistic is covered tomorrow. Then
in the
fine.
generalized linear model, we are going to cover it tomorrow.
That's great. That's great to hear then. Yeah.
Yeah, we are
Okay,
going
thank
to
you,
cover
sir.
the logistic as well as the basically the binomial and variable regression, Poisson regression. All these regression we are going to cover tomorrow.
That's good. Okay, then if there are no more questions, then I'm very much thankful to Dr. Shikhar and the Dr. Vinay, head of the department, for giving me this opportunity to share my thoughts on the regression analysis to all of the members who have joined virtually and other faculty members of this program. Uh, Thanks for the good, and I think should thank all the participants for good interaction. I really liked the way you interacted, and you have that interest to know more about the concept that I have delivered. Thank you.
Thank you, Dr. Vishnu Vardhan, for such an insightful and engaging session on regression analysis. Your deep expertise and clear explanations have provided us with the valuable knowledge and practical skills that will greatly benefit our academic as well as our research work. We truly appreciate the time and effort that you have dedicated to this session, and we look forward to applying that what we have learned today. Thank you once again for being with us and sharing your expertise. Thank you, sir.
Thank you. Yeah.
And
Thank
dear
you, sir,
participants,
for your
Thank you.
nice
Thank you, sir.
information and nice session. Thank you.
so dear participants, we will join tomorrow sharp at 6 p.m. where the topic will be generalized linear models, and this particular topic will be taken by Dr. Shikhar Tyagi, our organizer. So please tune in tomorrow at sharp 6 p.m. We
Why?
will we will we will we, we will be sharing the Google Meet link soon to all the participants. I request everyone, those who have attended today's session, to kindly fill the feedback form. If you have not received the feedback form, please reach out to us. We will be sharing it. So kindly fill the feedback form, and this will help you get the certificate. So thank you once again to all the participants. Thank you, sir.
Thank you,
Thank you,
sir.
one and all.
I have one
Thank you, sir.
point. I have
Thank
one
you, sir.
point. Okay, can you share that feedback form? I mean, feedback with me. I want to know about my session.
Sure, sir.
Sure,
We
sir.
will,
We will do that.
yes, sir.
Yeah, that will
We
help
will be
me
doing
to just plan it accordingly. Yeah, right. Thank you.
Yes, sir.
Sir, can we got recording of the sessions?
Yes, ma'am. You will get it after the.
Okay,
Just
sir.
after the workshop, we will share all the recordings with you together.
Okay, thank you, sir.
Good.
Thank you very much for
Wishes to the team. Okay, thank you.
Thank you, dear
thank you for the
participants.
information, sir.
Have a good night.
Thank you, sir. Thank you.
Thank you.